How's it going, guys? My name is Ashton. Today we're going to be discussing example 1.17 from our textbook. And then so far, we've given you a basic outline of what we have already. So we're going to have a container containing acetone and methanol in this liquid form. And we have a flow of air over top of it. And we're looking to find the molar fluxes of N2, N1, and N3. And then N3 was already stated in the problem. So the molar flux, I should say, of air is 0 already. And we also need to find the component profiles of each of methanol, acetone, and air. And the component profile basically is just saying it wants the molar concentration as we move up the container of our gas. So the way I've set up our container, we have starting at 0, and we're going to be going all the way up to a delta. And then any point at this is going to be Z. So I have our Stefan-Maxwell diffusivity equations already set up for us, because those take a while to write out and everything like that. And what we're going to do is we're going to use a root solver using software in order to find the mole fluxes of N1 and N2. But in order to do so, we need an initial guess. And then this initial guess and or estimate, whatever you'd like to call it, it needs to be accurate enough to the point where our order of magnitudes for them are so similar, or at least in the same ballpark, that we can hone in on the correct value and converge on the actual values. Because if our guess is so far in left field that we're never going to get there, so we need to ensure that our order of magnitude for those is very precise. And to do that, we can use scaling. And scaling is essential because say that we're giving our distance in light years or something like that, something outrageous, which would never happen. But through scaling, we can set everything from 0 to 1, and therefore get a nice little graph we have, and that way we don't have to have absurd units or anything like that when presenting information to others or colleagues or other professionals. We just have to create nice graphs that run from 0 to 1. So let's say we have our graph here, or not a graph here, but our container here runs from 0 to 1, we'll call delta 1. And then we can make a new variable, we can call this variable eta. So then, sorry, I gotta worship my whiteboard real quick. So we have eta, and that's gonna be equal to our any distance traveled, so our z component, over our delta, to give us a dimensionless number that runs from 0 to 1. And now, since we have this relationship set up already, and this scaling set up, so we have everything from 0 to 1, we can use that relationship and plug it into our Stefan-Maxwell diffusivity equation. And then using the chain rule, we can see that the change in molar concentration of component 1 over the change in our eta multiplied by our change in eta over our change in our z, or our distance traveled component. And a nice relationship we can see is, if we know, since we know eta is z over delta, we can plug that in and then actually take the derivative of it, and actually our z components will cancel out. So this further gives us 1 over delta times our change in molar concentration over our change in eta. Now, through there, we can look at the order of magnitude for it and relate it back to our Stefan-Maxwell equation in order to get a good estimate for our order of magnitude for our molar flux components of acetone and methanol. So rewriting our Stefan-Maxwell equation, so we have the change in molar concentration over our change in eta equals our molar concentration of 1 times our molar flux of 2 minus our molar concentration of 2 times our molar flux of 1 all over our total concentration times our Stefan-Maxwell diffusivity constant of 1 to 2, which was already given to us in the equation. And if you didn't have it already, you'd have to run a bunch of tests to find out, but it was given to us luckily. So now let's start by thinking about the magnitude that we know. So we know that the order of magnitude for our molar components So our molar concentrations is going to run from 0 to 1. And we know that our order of magnitude for our eta is going to run from 0 to 1. So we know that the order of magnitude for our change in molar concentration over our change in eta is going to be 1. So that means this entire thing, its magnitude, is going to be equal to 1. So rewriting we know that concentration basically is going to be equal to P over RT. And then our pressure over our R constant and our temperature, our pressure given to us is about 10 to the 5th pascals. And then our R component is going to be about 8. And our temperature, which was given to us, is about 300. So we have 10 to the 5th over 300 times 8, about 8. And then this is going to be about 10 to the 3rd. And then also, I couldn't forget, we have our delta under there as well. So looking at the order of magnitudes, we know from our bottom half of our equation that we have a 10 to the 5th over 10 to the 3rd, and that our Maxwell diffusivity constant is going to be, since it was given to us, we know, and since it's a vapor, we know this is going to be 10 to the minus 5 over our order of magnitude for our delta, as discussed earlier, is just 1, which is going to give us a total of 10 to the minus 3 at the bottom. And now looking at that, we have our molar concentration of 1 and 2 minus our molar concentration of 2, molar flux of 1 over 10 to the minus 3rd. And then we know the order of magnitude for our molar concentrations is just going to run from 0 to 1. So we're going to have 1 again and 1 again, giving us, and this is about, giving us a N, so our molar flux of 2 minus our molar flux of 1 over 10 to the minus 3rd. So that means that our order of magnitude for our molar fluxes is going to have to equal 10 to the minus 3rd. And with this guess, or this estimate for our initial molar fluxes, we'd be able to use our root solver in software in order to solve this differential equation and get the correct amount of molar fluxes after everything's run its course throughout the chamber or the container. And now, if you'll go to me with the next video, I can discuss the actual coding behind that and how we're going to use the root solver in order to get all of our molar fluxes and our component profiles and make a graph of them. So hang tight and we'll get to it. How's it going, guys? It's Ashton again, and right now we're on my desktop to do Python coding in order to solve the correct molar fluxes of acetone and methanol, as well as create the plot for the mole fractions of acetone, methanol, and air as the distance in the column or the distance in the container changes in their position respectively. So already I've imported some data from different things up here that I've already typed out, as well as I've defined all of the given information we have from the problem. But I'm going to walk you through each line. So the first line, we have import numpy as np, and then numpy just stands for numerical Python, and then Python also has a bunch of packages used to like solve initial value problems, to solve roots. They can make plots and everything like that. So I imported some of those from SciPy, which is one of the packages, a great package from Python. I imported a root solver, which is just scipy.optimize import root, and then I also imported an initial value problem solver, which is just the scipy.integrate and then import solve._IVP. And then to make plots of our data in order to display the mole fractions, I imported from plotly.subplots make subplots, and then I also imported plotly.graphObjects as GO or graphObjects or Go, whichever you want to. I'll refer to it as probably as Go. But that just allows me to make subplots. Allows me to make plots side by side one another, and the graphObjects allows me to add points and/or data to said plots in order to graph them.
And then I also like my graphs to be the darker color because I think it's more aesthetically pleasing. So I imported plotly.io as PIO in order to change the template, and I set the template to dark mode. So then from there we have the data that the problem gives us. So we have the Stefan Maxwell diffusivity constants that it gives us for each of the respective values. So we have, and those are in meters per sec or meters squared per second. We have the pressure, which is in pascals. We have the temperature, which is in Kelvin, and then we also have the universal gas constant, which is in joules per mole Kelvin. And then using PV equals nRT, we can actually solve for the concentration, and then our concentration is equal to our pressure over our universal gas constant times our temperature. We have our delta, which is the distance of the container, which is going to be 0.24 meters, as well as the simplified versions, as well as things I simplified for coding aspects, so I don't want things to get too hairy or too jumbled where I could make a mistake. So I defined F12, F13, and F23 as just being the concentration times their respective diffusion constants over delta, as well as we have our initial guesses for the mole flux of acetone, the mole flux of methanol, and then the initial mole fractions of acetone and methanol. So now we're going to start by writing the code in order to solve for the correct values. And so first we're going to start by defining our variable, which we're going to call, or defining our function, which we're going to call dy, with our dependent variable being eta and our independent being y. And then I'm also going to store actually our mole fractions of acetone and methanol. And for acetone, we're going to store it in the first plot of array, so we're going to call that 0. And then for methanol, we're going to store it in the second plot, which is y, which is the second component. And then since we know the mole fraction of air is going to be equal to 1 minus the mole fraction of methanol minus the mole fraction of acetone, it's because all the mole fractions are going to have to 1 to get the 1 for air, you just have to subtract the other two. And then we're going to also start by returning, and this is just going to bring our values back to us, so we have the ability to display them. And we're going to do np.array, because we're going to store our equation in an array, and then we're just going to use the Stefan Maxwell differential equations, which I have written down right here that I'm just going to copy in. And then those are going to be respectively for each component, or for acetone and methanol. So for acetone, it's going to be the mole fraction of acetone times the mole flux of methanol minus the mole fraction of methanol times the mole flux of acetone. And that's going to be over our simplified version of F12 from above. We're going to subtract our mole fraction of air times our mole flux of acetone over our F13. And for our second equation, we have that our mole fraction of methanol times our mole fraction of, or mole flux, I'm sorry, of acetone minus our mole fraction of acetone times our mole flux of methanol. I'm going to throw those in parentheses really quickly. We're going to divide that by F12, and then we're going to subtract the mole fraction of air times the mole flux of methanol over F23. And then before I forget, we're going to actually add in what our initial guesses are. So our initial guess for the mole flux of acetone was N1I. I'm just going to hard code these in real quick. And then our mole fraction, our mole flux, I'm sorry, for methanol is N2I. And with all that said and done, we can hit enter. And now we're going to solve our initial value problem in order to get the correct mole fractions for methanol and acetone as they diffuse up the container. So we're going to solve our initial value problem. So solve IVP, and it's going to ask for the function we want. And we call our function dy. and then after dy is going to ask for a span, and we're calling the base where the liquid first starts as 0, and then the top of liquid 1. So we're going to run from 0 to 1, and then it's going to ask for our initial concentrations, or initial mole fractions I should say. So we have our initial mole fraction of acetone, and our initial mole fraction of methanol, which are Y1I and Y2I respectively. And then from there, we're going to put dense underscore output. We're going to set that equal to true. And this will just give us the values back that we're looking for. So when we run that, we see that actually according to this, with our initial mole flux guesses, that our mole fraction of acetone is actually decreasing to the point where it's negative at the top, while our mole fraction of methanol is actually increasing to the point where it's above the value that it even started at. And while we know this is not the case, this just means that our initial guesses for the mole flux of acetone and methanol are wrong, but we can fix this by solving a root solver to find out when they're at the top, when their zeros are, in order to find what the correct values of those mole fluxes are. So what we have to do basically is we're going to put this back into our equation up here for our function, and then we're going to call this res, and that's just basically to store the values that we have here. And then once we have res, we want to actually return, and we want to return the res.solve at 1, because that's going to be the top of the container where they should be 0. So we're going to find out what those values actually are. And let's save that real quick. And it's going to go res.solve, and then we're going to say 1. We want that return value of 1. And we run into an error. Oh shoot. Tab that back over. Let's try that again. Unexpected indent. Alright, so according to this, it's saying that our mole fraction at the top of the container for acetone is going to be negative 0.2, while our mole fraction of methanol is going to be 0.86, which is should not be the case, as they should both be 0 at the very top at 1. So what we're going to have to do is add in a second equation in order to get the correct mole fluxes of acetone and methanol, and then we're going to use a root solver to find the roots like I stated earlier. So we're going to define this equation as f, with our variable being n. And then we're also going to take all of this, we're going to tab it over 1 to put it inside of our equation. We're going to run this really quickly. And then we're going to do res, which is just a variable store again. It's going to be root. And then for our root solver, it's going to ask what function we're trying to call. So we call our function f. And it's going to ask for our x naught, which is basically asking for our initial guesses or initial values for our molar fluxes of acetone and methanol. So we say the initial guess of molar flux for acetone and the initial guess for molar flux of methanol. We run that. And there's a mismatch, so that just means that my spacing is off somewhere. Let's try that again. Alright, awesome. So nothing came out, but we know it works since we've been getting errors, and we're going to go res.solve for x, or res x, in order to get the roots that we want. Great, so it gives us the initial roots now. Oh, whoops, this is wrong. I completely forgot I have to store these. We don't want those to be that anymore. We want them to actually store our roots. So we're going to store those new values in an array. We're going to store the molar flux for acetone at component 1, so our 0 point, and our molar flux for methanol at component 2, or our 1 point. So we're going to run that again. We're going to delete this. We're going to run this again. And we're going to find our root. So res.x. Alright. So now that we have those correct values, we can go in and we can set our N1. We can set that equal to, so our molar flux of acetone, we can set equal to our component inside of right here. So we want that, so we call it to our array res of dot x, and then we know it's the first component because it's acetone, so we're going to call it 0. And then we want our molar flux of methanol is stored in our res.x, and that's our second component, so 1. And now with those initial values set, we can copy this equation that we had before. We can put it into right here, and then this should give us the correct values. Awesome. So now with the correct values set for those, and then we have our output set, we can actually graph our data, because we found our correct molar fluxes for acetone and methanol now, and now we can finally graph our mole fractions of acetone, methanol, and air as they diffuse up the container. So to do that, we can start by eta underscore plot, and then we set that equal to np dot one linear space, and then we want it from 0 to 1. We want 50 points, and then we can do sol equals res dot solve of theta plot. Awesome. Okay, so there's just indentation error by me on accident. But now let's make our graph. So we're going to say fig equals make underscore subplot from our import above. And then it's gonna ask us for the rows. We want rows equals to 1, and then columns equals to 1. We're gonna add our individual data points we want to add. So fig dot fig dot add underscore trace, and then we're going to use our from above. Remember we had the graph objects, so we're going to go graph objects dot scatter because we want a scatter plot, and then our x is going to equal to our eta underscore plot. And then our y is going to be equal to our solution, and it's going to be our 0 component, because if you remember from up here we have our sol, so our sol solution equals res plot dot solve eta points, and our eta plot I should say, is our numpy, so our number dot line space, and then so that's basically just giving us a bunch of data points, 50 data points that we're going to collect, so it's going to do the first one in the array for the first 50 data points. And then we're going to call this name equals acetone. Now we're going to do the same thing for our methanol. So we're just typing out the exact same thing, except for we're going to change x is going to be equal to eta underscore plots again. And then our y is going to be equal to our solution array, but it's going to be this second component, so our 0 point. And then we're also going to have our name. We're going to set it equal to methanol. This is going to give me an error, I already know it. Go to the back. And then we're also going to graph our air as well. And an easy way to do that is just to copy this, paste it, and then since we know our y, it's going to be 1 minus that data point minus our data points from acetone, which is our 0. So that'll give us the graph of our mole fraction for air, acetone, and methanol respectively. So let's shift enter. Alright, now if you can see on this graph, we have that at the very tippy top at the 0.24 meters, or I'm sorry, at 0.24 meters, we have our mole fraction of, oh, whoops, I forgot to change this to air, because that would not make sense. But saying like that does not compute. Alright, now it makes sense. Okay, so it makes sense because at 1, or at the top of our container, our mole fraction of air is 1, while our mole fraction of methanol and acetone are below there. Hold on a second. Something doesn't seem right here. No, it seems right. Never mind. I'm just confusing myself. But yeah, that makes sense because we have this, and then basically as we travel, we're going to see a decrease in the amount of air when we go down more towards the base of our container, but when more at the top, we're going to see more of the air. So, I hope you guys learned something, a little coding today, and if you have any questions, please feel free to shoot me a comment or something like that, and thanks for watching.